And let me share my screen. And first, again, I want to go back to this kind of timeline. The chapter 14 homework is due on the 3rd, and chapter 12 must be done by the end of the day on the 3rd. That's Monday. The final needs to be done. It will be available from Monday till the 6th, and that's Thursday. Well, we don't meet on Thursday. I had thought that I would give you that extra day. Both of these will be due by 11:59 p.m. Again, we had said that the final will be optional. If you take the final, we'll drop your lowest test grade. If you don't take the final, we won't drop your lowest test grade, which is kind of like saying the final would be your lowest test grade. Today, we're going to finish looking at the notes in the packet. On Friday, we'll answer whatever questions you still have from chapter 14. And then the rest of Friday, Monday and Wednesday, we'll review for the test. Again, the best way to review for the test is to look at your back tests, because every test on the final exam is taken off of a previous test. The final exam will have 33 questions, I believe, going on memory. And again, they're all will be questions that you've seen before on the other tests. We left off last class looking at that definition of permutation and combination, and we did a couple of examples of evaluating them. Not many. Most of what we'll be doing, there's one more formula that we need to look at, and that's finding permutations with repetition. After that, we'll just be looking at examples. Before we do that, does anybody want to look at anything from any of the homework questions before we begin?
Can we look over 753, question 16A?
Okay, so page 753. 53, you said, right?
Yep, 753.
Question number 15, I believe is probably on that next page. What is the probability at a randomly drawn card hand of 5 cards contains all red cards, hearts or diamonds?
It was question 16.
Okay, thank you. I don't remember assigning 15. What's the probability that at least 2 people in a group of 4 have birthdays in the same month? Well, at least 2 people having birthdays. You know what? Let me go through. Is this going to let me do this? No, it's the camera's gone. It's not going to let me take that picture. At least 2 people in a group of 4 having birthdays in the same month. I'm going to add down here a page at the bottom. Probability at least 2 in a group of 4 have birthdays in the same month. So there could be 2 people with birthdays in the same month. There could be 3 people with birthdays in the same month, or there could be 4 people with birthdays in the same month. That's kind of all of the possibilities, except the complement of that would be none of them have birthdays in the same month. So we're going to say that that's 1 minus the probability that none have the same birthday month. And so that'll be 1 minus, well, for the probability of them to have a different birthday month, there's 12 months in the year. The first person could have their birthday in any month. There's still 12 months in the year. But the second person, they have to have a different month. So there's only 11 left to pick from. The third birthday person, there's still 12 months in the year, but they have to have a different month. So they only have 10 left to pick from. And then that fourth person, there's still 12 months in the year, but they can't have any of the same months as the other. So there are only 9 left to pick from. And I am perfectly fine if you just write this expression. If you want to, you can go through and multiply it out, but I'm fine if you just leave your answer here. That's what I'm looking for the reasoning of the problem. Does that make sense?
Yes.
So what I'm looking for there is the idea that it's the complement of each of them having a different birth month, and to find the probability of each of them having the birth month, you're going to find that probability for each individual person and then multiply. Okay, better?
Thank you.
You're welcome. Does anybody want to look at any other homework questions?
We look at number 1 and 2. I don't understand those.
On which page?
753.
Okay. These are asking you to evaluate permutations and combinations. Are you all right if we just do a couple of them?
Yeah.
Okay, so I am going to, do you have your book open?
Yeah.
Can you read to me 1A?
P parentheses 7, 3.
Okay, again, P means it's a permutation. It means from 7, we're picking 3. And so remember we had said that if we're picking 3, we'll take 3 factors, starting with 7. So the first number tells me where to start. And the second number tells me how many factors. And so let's see, 6 times 5 is 30, times 7 would be 210. And I think that was kind of where we left off last time with the permutations. Do you want to read me another one, please?
D C parentheses 7, 3.
Now, this one's different because this one's a combination. And we had said that combinations are a smaller number than permutations, but they're related. And so combinations, we're going to make a fraction. This number factorial goes in the denominator. So 3 factorial would be 3 times 2 times 1. And then in the numerator, we're going to put the corresponding permutation for the 7 times 6 times 5. And so that would give me, I'm going to look at that as 7 times 6 times 5. Over multiplying the denominator out, I'll get 6. And so that's just 7 times 5, or 35.
Okay.
So goofy things, permutations with a P is just the product, combinations with a C, you've got that bottom to it. You have to divide by. I had a student once when I taught high school that, goofy ways to remember. P's have no bottoms because you have to take off your bottoms to go pee. Don't shoot the messenger. It's a silly thing to remember, but it helps. Did you want to try one more?
Number E, the letter E, C 7, 7.
combinations of 7 things. Denominator is going to be that 7 factorial. Numerator always has the same number of factors as the denominator, starting with 7. Hey, wait a minute. Because they're both 7, both the numerator and denominator are the same. So that's just 1. Okay?
Okay. Thank you.
Anybody want to look at anything else from the textbook? Not hearing any. Go ahead.
Can you go over question 40 on the same page?
40. Okay. Okay. California originally operated a 649 lottery, meaning the grand prize went to a player or players who picked the same 6 numbers that were later drawn at random from a set of numbers, 1 through 49. In 1990, California went to a 653 lottery, but later the state went to a 651 lottery. Find the probability of winning a 649 lottery. With this, what you have to remember, with a lottery, we're going on the assumption that for a lottery, order does not matter. And so the sample space for that 649, if order does not matter, it's a combination. And so that would be from 49. I'm sorry, it would help if I wrote correctly. Let's try that again. From 49, I want to pick 6. And so that would be 6, 5, 4, 3, 2, 1 in the bottom. And in the top, I'd have 49 times 48 times 47 times 46 times 45 times 44. And no, I don't expect you to figure this one out by hand. You can use a calculator to find those products. So that's the number of ways of doing it. There's only one winning combination, so the probability of winning would be 1 over that answer. This one, the probability would be 1 over, well, they increased the number of choices, so it would be 53, combination 6. And this one would be 1 over combination 51, 6. And what you'll find is 49, 6 is the smallest number. 53, 6 is the highest number. So this one has the highest probability. This one has the lowest probability. And so this one is somewhere in between. So guessing, they probably went from the 53 to the 51 because not enough people were winning. They had to give it better chances. Does that make sense?
Mm-hmm.
Okay, great. Then let's go and look back at the notes. Can I clear this?
Yep.
1 sec.
Go ahead. I can't hear you.
Never mind.
Okay. Then let's go back to where we left off with those definitions of permutations and combinations. And let's look at that next page which is somewhat like what we just did, looking at applications. So here it says the Stamp Club has 9 members, including its president, Alicia. A 4-person refreshment committee is to be formed. How many committees include Alicia? Well, general rule of thumb, when I look at a committee, for a committee, order does not matter. So we're going to use a combination. Second thing I want to notice is this says how many. Since it says how many, each of them say how many, they're telling me that my answer is a counting number, so it won't be a fraction. I'm going to start with this one looking at part C first. How many committees are there altogether? Well, we said it's a combination. We have 9 members, and we want to choose 4. So 9 combination 4, as we were just looking, that second number goes factorial in the denominator, 4, 3, 2, 1. And we want the first 4 factors of 9 factorial in the numerator, 9, 8, 7, 6. I have a tendency to try to reduce these before I multiply. And so I'm going to say that 4 times 2 is 8. And then I'm going to say that 3 goes into 6 twice. And so 9 times 7 is 63, times 2 would be 126 committees altogether. So that's part C. Part A, if I want to have Alicia, that means that I'll have Alicia and 3 other people. And so there's 1 Alicia.
Mr. Ella,
Go ahead.
I have to leave for class for a little bit.
Okay,
Okay.
make sure you watch the video. And then I want 3 others from the 8 that are left. So that would be 1 Alicia and 3 others would be 8 combination 8, 3. And so that would be 1 times that combination. My denominator would be 3, 2, 1. My numerator would be 8, 7, 6. 3 times 2 times 1 is 6. So that cancels and I'm left with 56. For part B, without Alicia, well, without Alicia, there are 8 other people and we want 4 of them. So that would be combination 8, 4. Again, the smaller number is my factorial in the denominator, 4, 3, 2, 1. And I want the first 4 factors of 8 factorial. So that's 8, 7, 6, 5. Here, 4 times 2 would divide out the 8. 3 goes into 6 twice. So I have 7 times 10, or 70. Now, I'm going to go back to part C. And they ask you to answer that 2 ways. One way is to say there are 9 people. Combination 4 is 126. The other way that's sort of interesting is to say, well, if there's 56 committees with Alicia and 70 without Alicia, wouldn't the total number of committees be the 56 plus the 70 or the 126? Kind of cool. And again, a couple of things I want you to take away from this question. One is, remember, something like a committee or something like playing cards or something like picking numbers for your lottery, our order does not matter. So it's a combination. The other thing, pay attention. If a question says how many, our answer are counting numbers. If a question says what's the probability, then our answers must be fractions. Is this question all right, folks? Then next thing that I'd like to look at is that last formula, permutations with repetition. And so how many ways can I arrange the letters of the word dog? Well, if I'm looking at the different arrangements, because I guess spelling matters, order matters. So it's a permutation. So in the word dog, there are 3 letters, and I want all 3 of them. So that's 3 times 2 times 1, which would give me 6 ways. So if I tried to list them, the obvious is D-O-G. Then I could keep D first and switch the other 2, G-O. Or I guess I could put O first and I could have O-D-G. Or I could have O first and have O-G-D. Or I could have G first and have G-O-D. Or I could have G first and have G-D-O. And so we've got 6. We can use permutations because they're all different. Now here, what if instead, that shouldn't be work, that should be word, I'm sorry. I have the word all. Well, it's sort of a permutation, but you notice 2 of them are the same. So let's try making that list. I could have A-L-L. If I swapped the L's, it wouldn't look any different, would it? I could have L-A-L. I could have L-L-A. Are there any others? I don't think so. So there are 3 ways. And so do you see how by comparing all to dog, if some of the letters are the same, it's a smaller number. And so if I have permutations, arrangements where order matters, but some repeats, we're going to have a different formula for this. Let me write the formula in a sentence, and then let me apply it to that next one, Mississippi, so you see what it means. So I want the arrangements of n objects where R are the same, S are the same, T are the same, and I'm going to put dot, dot, dot. I'll have n factorial over R factorial, S factorial, T factorial. Let me give you a minute to write that out, and then let's apply it to our word all, and then apply it to that next word, Mississippi. Everybody ready? all has 3 letters, and 2 of them are the same. So that would be 3 factorial, 321, over 2 factorial, 2, 1. And so that would give me that 3. And with all, only 1 letter repeats. And so I only need that 1 factorial in the bottom. As opposed to if I look at Mississippi. In Mississippi, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters. And so that tells me I'm going to have 11 factorial in the numerator. Now, some letters repeat. Let's see, I's repeat. There are 4 of them. So I need a 4 factorial for the 4 I's. S's repeat. Let's see, there are 4 S's. So I need another 4 factorial for the S's. Anything else repeat in Mississippi?
The P's.
The P's. And how many P's are there? 2. So I need a 2 factorial for the P's. And so do you see why there's all those different factorials in the denominator? Because it depends on how many things repeat. And so to work this out, it would be 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3. Well, I got to move over. Times 2 times 1. Over in the denominator, I'd have 4, 3, 2, 1. Then I'd have 4, 3, 2, 1. Then I'd have 2, 1. When I first look at that, the arithmetic looks overwhelming. But let's notice that some of these numbers can cancel each other out. So you see how 4, 3, 2, 1 would divide 4, 3, 2, 1 here. Then let's see, I could take the 4 times 2, which gives me 8. Then I could take the 3 times 2, which gives me 6. And so I'm just left with 11 times 10 times 9 times 7 times 5, which is a smaller product. Is everybody all right if, in the interest of time, I don't take the time to do that multiplication? Again, I used Mississippi as an example because I wanted to show you why there were so many different factorials in the denominator. Next one says, how many ways can you run 4 red flags, 3 blue flags, and 2 green flags up a pole if the flags are indistinguishable except for color? Well, how many flags are there altogether? The total number is 3, I'm sorry, I misread. Red is 4 plus 3 plus 2. And so altogether we have 9 flags. If they were all different, they'd be 9 factorial ways. But they're not all different. There are 4 that all look the same red, 3 that all look the same blue, 2 that all look the same green. And so that would give me 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 4 factorial is 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. And 2 factorial is 2 times 1. Four, 3, 2, 1 cancels out 4, 3, 2, 1. 3, 2, 1 divides out 6. And we can say that 2 goes into 8 4 times. So I'm left with 9 times 7 times 5 times 4, which would be 63 times 20. Well, 2 times 63 is 126, and then I'll add that 0. And you see how this is technically a permutation because order matters. But because some of them are identical, you can't tell if you're moving around the two, swapping a green with a green. So we've got that smaller amount, and we have to divide out for each thing that repeats. Any questions on that one?
No.
Great. Then let's look at some other questions, other examples of questions. This time, I have a jar of marbles, 4 red, 5 white, 6 blue. I'm picking 3 without replacement. I want to, here notation-wise, P stands for probability. And so because these are probabilities, we should expect our answer to be a number between 0 and 1, or a fraction. If I'm picking 3 without replacement, remember this is like our conditional probability. And so let's find the probability that the first one is blue. Well, how many marbles are there altogether? What's the total number of marbles? When I add those, I get 15. So the probability that the first one is blue is 6 out of 15. Now, what's the probability that the second one is blue? Aren't there only 5 blue left of the 14 marbles? And the probability that the third one is blue, wouldn't that be 4 out of the 13 that are left? And so I guess I'm going to do a little bit of reducing before I multiply this. Reducing, let's see. I think it's obvious that 5 goes into 15 3 times. I think that it's obvious that 3 goes into 6 twice. And then I guess I could put 2 into 14 7 times. And so that leaves me with 4 over, let's see, 13 times 7 would be 91. That one all right. So then what's the probability that I first get a red? Well, red, there are 4 out of the 15. Then a white. white, there are 5, but again, remember that there are only 14 marbles left. Then a blue, well, there's 6. And remember, there are only 13 marbles left. And I guess as I look at this, I've got the same factors in the numerators as the denominators. So this one would also be 4 out of 90. Is that one all right?
Yes.
Next one says, I have a class of 15 students, 10 girls and 5 boys. I picked 3 to do 3 different problems. Because the problems are different, we're going to look at this as a permutation. The order matters. We could set this one up like the preceding, but because order matters, let's go through and do it with permutations. It would be the number of ways we can get 3 girls over the number of ways we can get 3 students, all of the different selections of 3 from the class. Well, for 3 girls, because order matters, it's a permutation. There are 10 girls. I want 3. So that numerator would be 10 times 9 times 8. From the entire class, there are 15, and we're picking 3. So that would be 15 times 14 times 13. Please notice that gives us that same type of fraction. The first one being a girl is 10 out of 15. The second would be 9 out of 14. The third would be 8 out of 13. And is everybody all right? In the interest of time, if I just set this up and we don't do the computation, can everybody do that multiplication on their own later?
Do we have to reduce it or can we reduce it at the end?
You can reduce it at the end, but because I'm doing the multiplication without a calculator, I find that it's easier if I make this number smaller before I begin. Do you know what I mean?
Mm-hmm.
So. Next one asks 1 girl, then 3 boys. Well, the denominator is still that permutation 15, 3, or there's still 15 times 14 times 3 ways of getting those students. 1 girl, well, there's 10, and I want 1 of them. So that would give me the number 10. And remember that word and tells us we want to multiply. We want 2 boys. Well, there's 5 boys and I want 2. So that would be 5 times 4. Or because it's a permutation, we can look at it, the probability that the first one is a girl is 10 out of 15. Then for the next one to be a boy, there's 5 boys from the 14 students left. Then for the next one to be another boy, there's 4 boys from, I apologize, I said 13 and only wrote 3. 4 boys of the 13 remaining students. And again, you can go through and work that out. Also, I want to say on the test, I don't think there are any that have numbers quite this big, but on the test, if you just multiplied and didn't reduce the fraction, I'd be fine with that too. Okay. Next one, we've got that same class. So I'm going to say that, just remind us that there are 10 girls and 5 boys in the class. But what makes this one different is I want a committee. And because with a committee, order does not matter, it's going to be combinations. And so from the class, to get 6 girls, well, there's 10 girls and we want 6. That's what we want. But our sample space would be the way I could pick 6 kids from the entire class. So that would be a combination 15, 6. So a little bit of scrap work, combination 10, 6. In the denominator, I'd have 6 factorial. In the denominator, I'd have 10, 9, 8, 7, 6, 5, 6 factors, starting with 10. The 6 and the 5 cancel out. I think I can also take the 4 and the 2 and divide that with the 8. And so let's see, that would give me 90 times 7 is 630 over 3. So there's 200 ways of getting, 210 ways, pardon me, of getting those girls. In the denominator, combination 15, 6. Since the smaller number is 6, we'll have 6 factorial in the denominator. Then we have 6 factors starting with 15. And so let's see, what are we going to do here? I am guessing, let's see, the 6 times the 2 would be 12. The, let's see, 5 goes into 15 3 times. So what do we have left here? In the denominator, I'd have 4 times 3 times 1, which is 12. In the numerator, I'd have to multiply 14 by, you know what? I'm going to just make these numbers a little bit smaller. 2 goes into 14 7 times and into 4 twice. 2 goes into 10 5 times. And the 3's cancel. And so what I would have is in the top 7 times 13 times 5 times 11. And in the denominator, I'd have 1. And so again, I'm going to be a little lazy here and not multiply it out. I'll just leave that problem. But because it's a committee, it's a combination. Next one. What's the probability that I get all boys? How many boys are in the class? Five? 5 boys in the class? How many do I want on this committee? 6. So can I get 6 boys for this committee? Is it possible?
No.
No. If it's not possible, the probability is 0. And then the last one asks for the probability that I get 2 girls and 4 boys. Well, 2 girls, again, because it's a committee, it's a combination. There are 10 girls, we want to choose 2. That word "and" again tells us to multiply. Combination, there are 5 boys and we want 4. And then the denominator from the entire class, the whole sample space, would be 15 kids, choose 6. And so combination 10, 2 would be 10 times 9 over 2 times 1, or 90 divided by 2 is 45. Combination 5, 4, well, the denominator is 4 factorial. The numerator would be the first 4 factors starting with 5. And so that would leave me with 5. And the denominator, the combination 15, 6, we already found to be, what did we say it would be? 7 times 13 times 5 times 11. And I guess here the 5s can divide out. So we're left with 45 over whatever you get, taking 7 times 13 times 11. And so those permutations and combinations help us count the number of ways something is possible. Then, going on to page 12, we're not going to worry about odds and we're not going to worry about expected value. But I did want to look at this little blue box because I think it's a good summary of what you need for probability. Probability is 0 only if the event cannot occur. Probability is 1 only if the event always occurs every single time. So putting those pieces together, remember your answer for probability has to be between 0 and 1. It should always be a fraction. Probability of A or B is equal to the probability of A plus the probability of B. And remember, we have to subtract the chances that they occur at the same time. Probability for events A and B is the probability of A times the probability of B, given that A already occurred. And like with the birthday months, if I have complementary events, there's some of their probabilities is 1. So we can say that the probability of an event is equal to 1 minus the probability of its complement. Beyond that, the other thing that you need to remember is in order to count the number of ways an event can occur, we can use permutations when order matters. And we're going to use combinations if order does not matter. But again, those only work if the objects are different and they cannot repeat. We can't use the same object over and over and over again. And the other thing is if a question says how many, then you should have a counting number answer. If it says probability, your answer should be a fraction. And amazingly, I apologize, we ran over for a minute, but that was exactly where I wanted to end today. And oh dear, give me just a minute. Looking at the fact that we're not doing odds or expected value, I don't think I put any of those in the homework, but let me just double check. Page 763. All right. Let's go back up here to the top, page 763. The only one that I'm going to ask you to do is 14. We're going to cross out the others because I believe that most of them involve odds and, oh wait, no, take that back. Eight and 10 are expected value, 14 and 16 I'd like you to do, and 18 I'd like you to do. And 23 and 24, just skip those first three. I'm sorry. So 1, 8, and 10 do not do on that last page, okay? Any questions?
I came in late.
Yeah, let me make sure I got you on attendance, Jess.
Okay, thank you.
And otherwise, we will see you folks on Friday. We'll go over whatever questions you still have on the homework. But please, on that last page, skip 1, 8, and 10. Because they deal with odds and expected value, which we are not covering. Have a great one.
You too.
Bye.
Bye.